guys, welcome back to the channel. In this video we are going to discuss the double sideband suppressed carrier modulation system, and let's directly jump into the topic. So let's start with the title, why it is called as double sideband suppressed carrier. The double sideband name represents the sidebands of the signal after the Fourier transform, which we will see, and the suppressed carrier says that the carrier signal is not transmitted in this system. That means the power used for transmission of the carrier signal is saved in this system. So this is also a type of amplitude modulation only, but just the carrier signal is not sent with the message signal. So let's represent the message signal with m of t and the carrier signal with c of t. This is the message signal and this is the carrier signal. Let's see the block diagram, and this block diagram is for transmitter side block diagram. Here we will send the message signal to the amplitude modulator, and here we are having a local oscillator which will generate the carrier signal, which is C of t, and then this will give us the DSB-SC signal. DSB-SC signal is nothing but just the multiplication of the message signal and the carrier signal. The carrier signal can be written as cos of 2 pi fct. So the multiplication of these two will give us m of t into cos 2 pi fct. That's it. This is the DSB-SC signal. So the amplitude of the carrier signal is the linear function of the message. Let's say the AC is the carrier signal amplitude. This is the linear function of the message signal. That means as the message signal amplitude will change, in the same manner the amplitude of the carrier signal will also change. So let's see the time domain representation of this. Which is a sinusoidal signal. Here we can see that here we are having a zero crossing. That means the signal is crossing t is equals to 0. So this is the carrier signal. The carrier signal will be having no information in it. It is just the signal which will help the low frequency signal to travel through a long distance. The carrier signal will be having constant frequency, constant amplitude and constant phase. So when these two are multiplied, this is the message signal, right? This message signal we are passing through this, and this is the carrier signal we are passing through this. So the amplitude modulator will multiply these two message signals, and we will get the output as the amplitude of the carrier signal will change. As we can see here, we are having a zero crossing. So here the phase of the signal will be get shifted by 180 degrees. So it will get reversed. The phase of the signal will get reversed. So when we flip this signal by 180 degree like this, then we will draw the signal. So it will, like from here it ended, we will start it from here, not continuously like this. So it is having 180 degree phase shift. So this is the modulated signal of t. This is the carrier signal and this is the message signal. So at t is equals to 0, the phase is reversed by 180 degrees. That's it. So let's see the frequency domain representation of this. According to the time shifting property of Fourier transform, we can say that m of t will give us m of f. In the same manner, m of t cos 2 pi f naught of t will give us 1 by 2 m of f minus f naught plus m of f plus f naught. So let's see further the representation in the graph. So let's see the frequency domain representation of DSB-SC signal. As we said, according to the frequency shifting theorem of Fourier transform, this signal will get shifted like this at the frequency f naught, minus f naught and plus f naught. So this is the signal, and after getting shifted it will look like this. Here you can see there is no discrete function, discrete representation of any signal, which represents that there is no carrier signal in this. So this is the upper sideband, and this is also the upper sideband, and the inner one are lower sidebands. So you can clearly see that there are two sidebands and no carrier. That's why this system is called double sideband suppressed carrier. So this is 1 by 2 m of f minus f naught, and this is 1 by 2 m of f plus f naught. So here in this system the f0 frequency is greater than b. How? See, this b is here from here, and this f0 is at large distance from b. Like here the b is and here it is the f0. So these two signals are not getting overlapped. If we take, if f0 is less than beta, then what will happen? Then this is the signal, normal signal, and when this is shifted by the frequency, this is f0 which is less than b, this is plus f0, so the signal will come like this. So you can clearly see that the two signals are overlapping each other in this region, due to which the message will be lost during modulation, and this cannot be recovered at the receiver end. So that's why, to neglect these things, the f0 should be always greater than b, and hence this is the modulation. Let's move to the demodulation process. So here at the receiver we are having synchronous demodulation. What is synchronous demodulation? I'll tell you. As we can see, the carrier signal is AC cos 2 pi fc and the phase is 0. So the phase is represented by plus phi, but here the phase is 0. So this carrier signal is the same carrier signal which we will use for demodulation. So let's draw the block diagram for demodulation here. This is the DSB-SC signal that we will give to product modulator, and then this signal will be passed to low pass filter, and then we will get the original signal, or you can say half of m of t. I will tell you the calculation of this, how it came. And from the local oscillator the carrier signal will be generated, that is C of t. C of t is AC cos 2 pi fct with same frequency and same phase. The phase is 0 here, so that's why we are not representing it. So let's directly write AC cos 2 pi fct. So this carrier and the carrier signal which we use it in modulation, both are same. That's why this demodulation system is called synchronous demodulation. So I have drawn the same figure here. We are giving the DSB-SC signal to the product modulator, and this is a local oscillator. The carrier signal is cos 2 pi f0 t. So in the product modulator, normally this signal and this signal will get multiplied. So let's denote the resultant signal as E of t. We will get mt cos 2 pi f0 t into this carrier signal cos 2 pi f0 t. So these both are same, you can see it. So we will write it as m of t, not t are same. We can write it as cos square of 2 pi f0 t, and we can write this cos 2 pi f0 t as 1 plus cos 2 of 2 pi f0 t by 2. So we will separate the terms, m of t by 2 plus m of t by 2 into cos of 2 pi f0 t. As we are passing this signal with low pass filter to the low pass filter, so the signal which are having high frequency means cos 2 pi f0 t is like cos 4 pi f0 t. So 4 pi f0 t is very high frequency, so this frequency signal will get rejected in the low pass filter, and only less frequency signal will get transmitted. So let's draw the signal like this is the signal we will get. This is half m of t, and these are the shifted ones, half of m f minus 2 f0 and half of m f plus 2 f0. This is at 0, this is at 2 f0, and this is at minus 2 f0. After the Fourier transform, we will get this as m of f by 2 plus half m of f minus 2 f0 plus half of m of f plus 2 f0. So this thing we are representing here. This is the middle one, and these are the shifted ones. That is, one signal is at 2 f0 and another one is minus 2 f0. So after passing this through the low pass filter, the high frequency signals will get rejected, and only the low signal frequency will be get at the output. So this is the low frequency signal, that is half of m of t. So that's why we got this at the output, and hence we have successfully demodulated the DSB-SC signal to the message signal. So in this type of system, the receiver is having synchronous demodulation. So because of this, the carrier should be same in the demodulation and also in the modulation system, because of which the complexity of the receiver increases. So this complexity of the receiver increases the cost of the receiver and the emitter. So the complexity also increases the cost, and this complexity is okay for point-to-point communication, but this is not okay if it is like for a broadcast system. Like if we want to broadcast something, there are so many hundreds or thousands of people who are receiving the signal from the broadcast system. So this is not okay for broadcasting system, because the cost of the transmitter is high and the cost of the receiver should be less, but here that is not the case. So this is the drawback in DSB-SC signal, because of which we will shift to the double sideband with carrier, that is pure amplitude modulation, in which the carrier signal will also be sent to the transmission system. So that's it for this video, guys. I will explain the double sideband with carrier or amplitude modulation in the next video. So stay tuned. If you liked the video, then press that like button and subscribe to my channel if you are new here. And yeah, bye.